In this presentation, we are going to talk about the book Advances in Financial Machine Learning, specifically on the Chapter 14 Backtest Statistics.
We're going to discuss the concepts behind Chapter 14, starting by the motivation of the author, following by the types of backtest statistics that can be categorized into general characteristics, performance, runs and drawdowns, implementation shortfall, return and risk efficiency, classification scores, and attribution. Motivation. In the previous chapters, we have studied three backtesting paradigms. First, historical simulations by the walk-forward method. Second, scenario simulations by the CV and CPCV methods. And third, simulations on synthetic data. Regardless of the backtesting paradigm you choose, you need to report the results according to a series of statistics that investors will use to compare and judge your strategy against competitors. In this chapter, we will discuss some of the most commonly used performance evaluation statistics. Some of these statistics are included in the Global Investment Performance Standards. However, a comprehensive analysis of performance requires metrics specific to the machine learning strategies under scrutiny. Types of backtest statistics. Backtest statistics comprise metrics used by investors to assess and compare various investment strategies. They should help us uncover potentially problematic aspects of the strategy, such as substantial asymmetric risks or low capacity. We can see on this slide the various categories of backtest statistics. General characteristics. The following statistics inform us about the general characteristics of the backtest. Time range specifies the start and end dates. The period used to test the strategy should be sufficiently long to include a comprehensive number of regimes. Average AUM, which is the average dollar value of the assets under management. Capacity can be measured as the highest AUM that delivers a target risk-adjusted performance. Leverage measures the amount of borrowing needed to achieve the reported performance. If leverage takes place, costs must be assigned to it. One way to measure leverage is as the ratio of average dollar position size to average AUM. Maximum dollar position size informs us whether the strategy at times took dollar positions that greatly exceeded the average AUM. In general, we will prefer strategies that take maximum dollar positions close to the average AUM, indicating that they do not rely on the occurrence of extreme events. Ratio of longs shows what proportion of bets involved long positions. Frequency of bets is the number of bets per year in a backtest. A sequence of positions on the same side is considered part of the same bet. A bet ends when the position is flattened or flipped to the opposite side. The number of bets is always smaller than the number of trades. Average holding period, it's the average number of days a bet is held. High-frequency strategies may hold a position for a fraction of seconds, whereas low-frequency strategies may hold a position for months or even years. Annualized turnover measures the ratio of the average dollar amount traded per year to the average annual AUM. High turnover may occur even with a low number of bets, as the strategy may require constant tuning of the position. Correlation to underlying. It's the correlation between the strategy returns and returns of the underlying investment universe. When the correlation is significantly positive or negative, the strategy is essentially holding or short selling the investment universe without adding much value. Performance statistics returns numbers without risk adjustments. Let's take a look at some useful performance measurements. P&L, or profit and loss, is the total amount of dollars generated over the entirety of the backtest, including liquidation costs from the terminal position. P&L from long positions is the portion of the P&L dollars that was generated exclusively by long positions. This is an interesting value for accessing the bias of long-short market-neutral strategies. Annualized rate of return is the time-weighted average annual rate of total return, including dividends, coupons, and costs. Hit ratio is the fraction of bets that resulted in a positive P&L. Average return from hits are the average return from bets that generated a profit, and average return from misses, the average return from bets that generated a loss. Time-weighted rate of return is the rate from realized and unrealized gains and losses, including accrued interest, paid coupons, and dividends for the measurement period. GIPS rules calculate time-weighted rate of returns, or TWRR, adjusted for external cash flows. Periodic and subperiodic returns are geometrically linked. For periods beginning on or after January 1st, 2005, GIPS rules mandate calculating portfolio returns that adjust for daily weighted external cash flows. We can compute the TWRR by determining the value of the portfolio at the time of each external cash flow. The TWRR for portfolio I between subperiods T-1 and T is denoted R and can be calculated by dividing the market-to-market profit or loss for portfolio I at time T and the market value of the assets under management by portfolio I through subperiod T. Cash inflows are assumed to occur at the beginning of the day and cash outflows at the end of the day. These sub-period returns are then linked geometrically as phi, which is the product of the time-weighted rates of return. The variable fee can be understood as the performance of $1 invested in portfolio I over its entire life, which starts at period 1 and ends at period T, capital T. We can see then on the slide the annualized rate of return of portfolio I. Runs. Investment. Given a time series of returns from bets, we compute two weight series, W- and W+. Inspired by the Erfindel-Hirschman index, for W plus bigger than 1, we define the concentration of positive returns as H plus and the equivalent for concentration of negative returns as H minus. From Jensen's inequality, we deduce that the squared expected, the TWRR, is smaller than the expected value of squared TWRR, which is then smaller than the squared expected TWRR of vector of size R plus. This deduction has an equivalent boundary on negative bet returns. These definitions have a few interesting properties. The first, the H plus is between 0 and 1. The second one, we have uniform returns, and on the third one, we have only one non-zero return. So ideally, we are interested in strategies where bets returns exhibit high Sharpe ratios, high number of bets per year, high hit ratios, low H plus, low H minus, and low HT. Bets are not concentrated in time. Drawdown and time underwater. Intuitively, a drawdown is the maximum loss suffered by an investment between two consecutive high watermarks. The time underwater is the time elapsed between an HWM and the moment the P&L exceeds the previous maximum profit and loss. Figure 14.1 provides an example of a drawdown and the time underwater. On this slide, we can see some code. On snippet 14.3, the code implements the concepts of returns concentration and derives a similar expression for the concentration of bets across months, HT. On snippet 14.4, the code derives both drawdown and time underwater series from either the series of returns or the series of dollar performance. We can see here some useful measurements of run statistics for performance evaluation, such as the Herfindahl-Hirschman index on positive returns, negative returns, time between bets, and finally the 95 percentile drawdown and time underwater.
Implementation shortfall. Investment strategies often fail due to wrong assumptions regarding execution costs. Some important measurements of this include the broker fees, are fees that are paid to the broker for turning the portfolio over, including exchange fees. Average slippage per turnover are execution costs, excluding the broker fees. For example, it can include the loss caused by buying a security at a fill price higher than the mid price at the moment at the order was sent to the execution broker. The dollar performance is a ratio between dollar performance and total portfolio turnovers. It signifies how much costlier the execution could become before the strategy breaks even. Finally, the return on execution costs is the ratio between dollar performance and total execution costs. It should be a large efficiency. Until now, all performance statistics seen in Chapter 14.4 considered profit, losses, or costs. In this section, we account for the risks involved in achieving those results. The Sharpe ratio is defined as a ratio between the mean and the standard deviation. The purpose of this ratio is to evaluate the skills of a particular strategy or investor. Since the mean and the standard deviation are usually unknown, the true ratio cannot be known for sure. So, there is a consequence that these ratio calculations may be subject of substantial estimation errors. The probabilistic Sharpe ratio is a ratio that provides an adjusted estimate of the Sharpe ratio by removing the inflationary effect caused by a short series with skewed or fat tail returns. PSR estimates that the probability that the observed Sharpe ratio is greater than the benchmark Sharpe ratio. In this function, Z is a cumulative distribution function, T is the number of observed returns, gamma 3 is the skewness of the returns, and gamma 4 is the kurtosis of the returns. In this image, we can see the PSR increases with a greater Sharpe ratio, or longer track records, T, or positively skewed returns and decrease the fatter tails. The deflate Sharpe ratio is a PSR where the rejection threshold is adjusted to reflect the multiplicity of the trials and is estimated by the variance across the trials, and N is the number of these independent trials. Z is the standard normal distribution and gamma is the Euler-Mascheroni constant. The logic behind this ratio is that given the Sharpe ratio estimates, it is expected a maximum greater than 0, even if the true Sharpe ratio is 0. The Sharpe ratio increases quickly as more independent trials are attempted, bigger the n, or the trials involve the greater variance. Efficiency statistics. The annualized Sharpe ratio is a Sharpe ratio value annualized by a factor of a square root of A, where A is average number of returns observed per year. The information ratio is the annualized ratio between the average excess return and the tracking error. And this error is estimated as the standard deviation of the excess returns. The probabilistic Sharpe ratio corrects the Sharpe ratio for inflationary effects caused by non-normal returns on track record lengths. It can be computed on absolute or relative returns. The deflated Sharpe ratio also corrects the Sharpe ratio from inflationary effects caused by non-normal returns, track record lengths, and multiple testing selection bias. It also can be computed on absolute or relative returns. Classification scores. In the context of meta-labeling strategies that we can see in Chapter 3, it is useful to understand the performance of the machine learning overlay algorithm in isolation. In these strategies, the primary algorithm identifies opportunities, and the second, overlay algorithm, decides whether to pursue them or to pass. Accuracy is the fraction of opportunities correctly labeled by the overlay algorithm, where TP and TN are true positives and negatives, and FP and FN are the number of false positives and false negatives. Precision is the fraction of true positives among the predicted positives. And finally, recall is the fraction of true positives among the positives. F1 comes when accuracy may be not an adequate classification score for meta-lab applications. We need to suppose that when there are more negatives than positive cases, a classifier predicts every case to be negative will achieve higher accuracy, even though the recall will be 0 and the precision undefined. In the case of more positive cases than negative cases, a classifier predicts all cases to be positive will achieve true negatives and false negatives equal to 0. The conceptual difference between accuracy and negative log loss is that not only whether our predictions were correct or not, but the probability of those predictions as well. In this table, we can see how F1 score is defined in different cases. When there are no true negatives or false positives, the precision is a positive real number between 0 and 1, and accuracy equals recall. When there are no true negatives or false negatives, the precision is also a positive real number between 0 and 1. Recall equals 1 and accuracy equals precision. Attribution. The purpose of performance attribution is the decompose of the profit and loss in terms of risk classes. For example, a corporate bond portfolio manager typically wants to understand how much of the performance comes from his exposure to the following risk classes: duration, credit, liquidity, economic sector, or currency. These risks are not orthogonal, so there is always an overlap between them. It's our interest to attribute P&L across categories within each class, and these can be accomplished as follows. First step is to avoid the overlapping problem. We need to make sure that each member of the investment universe belongs to one and only category of each risk class at any point in time. Second step is for each risk class, we form one index per risk category. After that, we repeat the same step, but in this time we form those risk categories indices using weights from the investment universe and rescaled so that each index weightings add up to 1. Finally, the excess return of a short duration index is a return using portfolio weightings calculated in step 2 minus the returns using the rescale universe weightings calculated in step 3.